In this video, I provide a derivation and some applications of the envelope theorem. I hope that this video will provide you both with an understanding of why the envelope theorem works the way it does and where we can apply the envelope theorem. Here's the setting. Suppose that you want to maximize a function with respect to x and perhaps subject to some constraint. The constraint and the objective function are both functions of a parameter alpha. We could set up our Lagrangian. And if we wanted to solve this optimization problem, we would take first order conditions with respect to x and with respect to mu. And so these two equations will hold. When these hold, will give us the optimal x as a function of the parameter and the optimal Lagrange multiplier as a function of the parameter. So these two equations, I'm going to set these aside. Now with the solutions to this optimization problem with both the Lagrange multiplier and the control variable x, we could plug in to just make this Lagrangian a function of the parameter. Okay, so now we have the first order conditions from our constrained optimization problem, and we can plug back in to get our, what I'll call the total Lagrangian. Now the proof will proceed in two steps from here. First things first, and this is going to be our first step, we're going to notice that this total Lagrangian can be thought of just as a function of alpha, what I'm going to think of as the partial Lagrangian. Second first order condition, when we evaluate at the optimal value when this actually holds, actually wipes out this second term. So all we have to do is have this function here. And we're going to be interested in the total effect of alpha on this function. That's going to be the function f star. This is the optimized objective value as a function of alpha. Now we know that it is true that f star, our optimized objective value, is identically equal to the partial Lagrangian. So we can take the derivative and we can see what we get here. We're going to be interested in this total effect derivative. How much does alpha move around that optimized objective value? So that's the first step, is that we can establish this equality. Now this is going to be an important equality, so I'm going to set it off to the side. Okay, so now step 2 of this is to take a look at our total Lagrangian and see all of the different ways that alpha can affect that. So let's just take the total derivative of our total Lagrangian equals. Now that's just the total derivative of our objective function. We can do the derivative of this second term now. Now that's a lot of terms that have popped out there. Let's go ahead and group them in a nice intelligent way and we'll see how things work out. So first things first, I want to group terms on dx d alpha. Now dx d alpha multiplies df dx. So it also multiplies dgx times mu, and there's going to be a minus sign there. The next thing I'm going to do is I'm just going to recopy this term here, and then I'll just take the rest of the terms and put them kind of off to their side. Okay, so now we have these terms arranged a little bit better way, and what we can see is that in this expression a lot of things are going to cancel out. First things first, if we see equation 1, that's from our first order condition with respect to x, that's going to make this term here equal to 0. Second thing is that our constraint holds, and that's actually our second first order condition from this. We'll have that second term equal to 0. So we get a whole bunch of terms that end up wiping out. And this is the end result. Taking the total derivative of our total Lagrangian just has direct terms left over. If we just looked at our original Lagrangian as a function of alpha and we took the derivative with respect to alpha, this is what we would get. There are no chain rule terms left over. Those first order conditions knocked them all out. So really what we've established here is that this is our partial Lagrangian. Is that this partial Lagrangian, the derivative of that with respect to alpha, equals the total derivative of the objective function with respect to alpha. First things first, you identify a derivative of an objective function with respect to a parameter that you are interested in knowing about. Second thing is, you write out your Lagrangian. Third, you take the partial derivative of your Lagrangian with respect to the parameter that you're interested in seeing what happens to the objective function. Fourth, once you do that, you evaluate at the optimal values. That gives you this equality between the partial Lagrangian and the total Lagrangian. Fifth, you interpret what you get. Now that is what you'll get, and that is the beauty of the envelope theorem, and that is how you use it. First result is, suppose we have a utility maximization problem in the background, and we want to know, well, what is the marginal utility of income? Well, that's something that we can actually find in the math now. So let's go ahead and write out the Lagrangian. Let's appeal to the envelope theorem. What we want to know is we want to know, how does my maximized utility change when I change income? As the envelope theorem tells us, is just take the partial derivative of Lagrangian with respect to income, and then evaluate at the optimal value. Income only shows up once, and what we'll get is that that equals lambda. But it's not just any lambda. What we have to do with the envelope theorem is then evaluate at the optimal value. Marginal utility of income is this lambda function. It is our Lagrange multiplier in the constrained optimization problem. So there's application number one. Let's do a second application here within the utility maximization problem. Suppose that you go ahead and solve for your maximized utility, and you get your indirect utility function. Is there a way to go from there to get my demands? But let's go ahead and appeal to the envelope theorem and see what we can get. Now, remember our Lagrangian. Let's just take the partial Lagrangian with respect to, let's say, the price of x, and see what pops out. Take the partial Lagrangian with respect to px. What we'll get is we'll get a lambda times x. Now let's just, for the heck of it, apply the envelope theorem to this. Once we evaluate at the optimum, well, x star is what we're after. See, notice we want to know, how can we get from indirect utility function to something like an x star? Well, we're kind of halfway there. Notice that the envelope theorem would tell us what we can do is take this equation and rearrange it a little bit. This is x star equals, let's divide by a negative lambda, divided by a negative lambda star, dv dpx. But this lambda star, remember, is the marginal utility of income. And remember, we can get that from just taking the derivative of our indirect utility function with respect to income. That was the previous result. So, we get this sort of weird looking identity here. That we can just take the derivative of the indirect utility function with respect to price, divide that by the derivative of the indirect utility function with respect to income, take the negative of that, and we get our Marshallian demand for the good that we took the derivative with respect to the price. So, that's a really cool result, and it is an application of the envelope theorem. Moreover, it has a name. This is Roy's identity.